Thank you for a kind introduction by Toda-san. My name is Takaya Noda from Hitachi-GE Nuclear Energy, and I belong to the Global Business Development and Management Division. And I am now working for BWR X300 project. So I'm an interface of GE Hitachi. So GE Hitachi and Hitachi-GE, we two companies are developing BWR X300. And prior to this BWR X300 project, I had been working for Horizon UK project as a member of business development team. So today's presentation, I would like to talk about Hitachi-GE experience in BWR construction and recent activities. Okay, so this slide shows the contents of today's presentation. So firstly, I briefly explain about Hitachi-GE overview, and then I will touch on Hitachi-GE experience, and then move on to the BWR X300 and HGNE contribution to the project. And finally, I will make a closing remarks. Okay, so I start with Hitachi-GE overview. So maybe this slide is the most important point of today's presentation. So this slide shows Hitachi and GE Vernova Global Nuclear Alliance. So as this top left shows, we have GE Hitachi Nuclear Energy based in United States, and also Hitachi GE Nuclear Energy based in Japan. So both two companies have same parent companies, GE Vernova and Hitachi, but the percentage of shareholders are different. And this GE Hitachi Nuclear Energy is taking global BWR services and new plants. And my company, Hitachi-GE Nuclear Energy, is taking Japanese BWR services and new plants. So for example, if BWR X300 is built in Estonia, GE Hitachi will take a lead of this new build project. And if BWR X300 is to be built in Japan, Hitachi-GE will take a lead of the project. GE and Hitachi have a more than 50 years old technology relationship. And for nuclear part, we have over 40 years of partnership. And GE Hitachi and Hitachi-GE will have synergies and complementary capabilities between two companies. And we are now partnering on the most advanced operational reactors in the world today, so which is BWR X300. So, and then joint experience taken to the next evolution of reactors. So GEH and Hitachi-GE have own strengths in both companies. So GEH, their strengths in N-SSS design, and they are doing global business, so their strengths in global supply chain, and BWR OEM licensing experiences, and global nuclear experience as a whole. On the other hand, Hitachi-GE, we have the design capabilities, and we have factories in Japan, so we can manufacture key components of BWR reactors. And also we have a rich experience of construction in Japan for more than 40 years, and we can apply latest construction methods together with integrated CAE. And this slide shows Hitachi-GE business portfolio. So HGNE covers front new builds to back-end business in Japan. So as for new builds, multiple ABWRs are ready for operation, and we are currently focusing on the restart of existing plant. So we are now focusing on these maintenance services, especially for safety enhancement work for plant restarts and Fukushima decommissioning work. And once existing plant starts again, we can start outage and plant maintenance services. And also for backend, we provide component supply for Rokkasho reprocessing plant, and also we produce spent fuel interim storage casks. And this slide shows HGNE's vision of nuclear future. So value of nuclear power plant is to produce stable energy source to contribute to carbon neutrality. So we have constructed multiple ABWRs in Japan, which are large water reactor, and we are now developing so-called highly innovative ABWRs, so which equip global standard design based on Fukushima lessons learned and UK GDA experience, and installing new safety mechanisms. So this one is also large water reactor. And in addition to large water reactor, GH and HGNE are now developing BWR X300, so which will to meet the demand for small to medium power supply and replacement of old plants. So today's presentation, I will focus on this upper side of chart, so which is light water reactors. Then I move on to the Hitachi-GE experience. So Toba-san already explained about the continued construction experience of Japanese BWR plants. So HGNE's construction experience has begun in 1960s. Since then, HGNE have built more than 20 units of BWR construction experience over 40 years. And from 1990s, HGNE have built 4 ABWRs and additional 2 ABWRs under construction. So as Topa-san already touched on this, but Shimane 3 and Oma 1 and Higashidori is also next series of ABWR. So I can say we have continued experience of BWR construction, but I intentionally stopped this chart in 2010 because after Fukushima accident, we don't have new construction activities in Japan. So later I touch on what we did after Fukushima accident to keep our capabilities and knowledge for younger generation to take over our capabilities. Okay, so this is a brief introduction of ABWR. So HGNE's latest large reactor design is ABWR, which is most experienced generation 3 reactor in the world. So features of ABWR are safe, reliable, and cost competitive, simplified system with high operability, short and credible construction. And we got design certified by the US NRC in 1997, and the first license approved in 1991, and now we got 6 ABWRs in Japan. And UK GDA granted, we got GDA in 2017. So this is a picture of world first and second ABWRs, Kashiwazaki-Kariwa 6 and 7. So although ABWR is the latest design, it's been incorporating the various customer requirements and site-specific conditions in Japan and overseas. So starting from Kashiwazaki-Kariwa 6 and 7, each plant has each new feature, but important thing is that ABWR is proven technology, and ABWR can avoid FOAK risks. So HGNE's latest experience is the UK ABWR GDA, so which completed in December 27. So this is our track records of ABWR revolution. And this slide shows the UK ABWR overview. So UK ABWR improved the proven ABWR design in Japan by incorporating the Fukushima countermeasures and reflecting UK and European regulatory requirements. So UK ABWR applied countermeasures for severe accident as lessons learned from the Fukushima accident, alternative power supply and coolant injection from backup building, and protection from airplane crash, which enables the robust reactor building structures layout to protect the control building from airplane attack, and division segregation against internal hazards, robust I&C design, which satisfies the diversity requirement in the UK, and design with UK safety classification, and multiple safety systems, so on. And now we are developing highly innovative ABWR. We call it HI-ABWR. And the concept of HI-ABWR is further new safety mechanisms to implement it based on international standard ABWR. So likewise, UK ABWR, HI-ABWR equip the innovative safety system which are like intensified measures for natural disaster, terrorism, internal hazards, and also HI-ABWR will have passive safety system utilizing natural force and suppress influence on external environment at severe accident. So FCVS will be equipped for HI-ABWR. And the aim of this HI-ABWR is to support for the society to achieve carbon neutrality. Okay. And now I would like to move on to the new build construction challenges, which we had in the past experience. So new nuclear construction have big challenges, like historically, we face over schedule and cost overrun projects, especially for large reactor projects, and significant delays and rework due to many factors. So recently we see those things in US projects or European projects. And our approach for new construction is a comprehensive, detailed, well-coordinated project development phase prior to construction start. So we have the 4 methods to do this. So the first one is integrated engineering, design, and construction management process and tools. Project-specific detailed design, that is well advanced prior to construction. And also, of course, we have integrated project-specific supply chain. So this is the strength of Japanese industries. So supply chain plus logistics and scheduling. And project-specific IT solution implemented to the project. So project development phases are typically several years in duration. So this project development phase is very crucial. And as a result, we achieved on-time construction, and we could execute the project within budget. So this slide shows the track record of BWR on-time construction. So from Kashiwazaki 6 to Shika 2, the total planned duration and actual duration are exactly the same. So this is a great achievement of Japanese BWR projects. And I would like to emphasize that only HGNE, Hitachi, cannot make this on time and on budget construction. But we need a strong client, owner of utility, and construction companies, and very good suppliers. Only if we can have those companies, then I think we can make the project on time and on budget. And just one point, maybe as you can see, the figures of Hamaoka 5 and Shika 2 is slightly longer than Kashiwazaki Kariwa. Maybe I think this is the leveling of the peak number of staffs, and optimize the plant schedule. So this slide shows HGNE's construction strategy. So as you can see left hand of the slide, HGNE categorized nuclear power plant construction characteristics as large work volume. So the more than 1,000 people are working on site in the construction phase, and long period work, it takes more than 5 years, and many interfaces with project participants. So client, construction company, and HGNE and suppliers, and very, very many documents and records, and we need traceability. So we have strategy and methodologies to overcome these characteristics. The first one is improve on-site productivity. So we apply front-loaded construction engineering prior to start of construction. And we apply enhanced site communication and training plan. And also, we will reduce on-site work by applying modularization. So this is one of the features of SMR as well. And also, we use the leveling the on-site work by applying open top and parallel construction. And also, to improve site support work efficiency, we apply construction support systems. Then I think we can achieve the good safety, quality, and on budget and on schedule project. So the first strategy is front-loaded construction engineering. So compared to previous design process, front-loaded construction engineering begins in parallel with basic and detailed design. So advantage of this strategy is to reduce and minimize design changes during construction. Construction engineering to basic design, and then detailed design will give inputs from the plant design. So we make the circulation of construction engineering to basic design and detailed design to construction engineering. So this iteration and circulation of design process will result in improve on-site productivity by just do it as planned. So if we can fix everything before start of construction, we can make construction as planned. So this is our strategy of front-loaded construction. And this slide shows site overall meeting to improve integrated site communications. So from top management to quality, safety, and schedule, each member of projects will join in the same meeting to establish the same understanding and details of the project. So I think this is one of the feature and strengths of how Japanese project can make a integrated project, integrated team. So this is an example of communication during construction. And the next one is about modularization. So this slide shows concept of modular method. So by assembling and fabricating equipment, piping and valves and structures at a module fabrication shop, we can reduce the work on site, which will lead to the shorten on-site installation schedule and improve work safety and productivity. So for many years, HGNE have utilized this modularization method. So this is not a very new concept, but we have already implemented in the many projects in Japan. So this slide shows the image of module factory. So this is the inside of module shop to assemble equipment, valves, and others. So this module shop location is adjacent to port for direct transportation to the site. And the module shop needs to have enough space to store the components and the module considering custom clearance and capable lifting facilities for modularization. So this module shop will be located nearby the site. I think this is also good for local economy as well. And this slide shows the sequence of construction period. So nuclear power plant construction sequence has complicated critical and subcritical paths. Hitachi BWR construction sequence is proceeded concurrently with civil building works and MEH works. So by applying modularization and parallel construction approach, past projects could achieve short construction period. So the green activities are civil activities, and blue one is mechanicals, and the red one indicates critical path from rock inspection to fuel loading. So one of ABWR's features is that the critical path is composed of mainly civil-related activities. So this picture is mat module. So mat module installation, it is composed of mat, lever, and anchor bolts for pedestal and embedded plates, and so on. And this one is RCCB lower liner and HCU, CUW. So we have many large modules which already being used for the past projects in Japan. So these are example of large modules. So the left-hand side is a reactor building, and the right-hand side is a turbine building. So both buildings applies many large modules for construction of a BWR projects. And this slide shows open top and parallel construction method. So these figures shows the step 1 to step 6. And the summary of open top and parallel construction method is before close the shearing, which is step 3, we carry in the MH components, so which are equipment, large bore piping, steel HVAC ducts, platforms. We install them to the rooms before close the shearing. So we can do the concurrently with building works, MEH installation, and carrying in work can be proceeded. So blue one is civil construction, and the red one shows mechanical work. So from step 1, we will do the both civil and mechanical works in parallel. So this is open top and parallel construction method. And this is the image of open top and parallel construction method. So the upper side of the slide shows the image of sequence of the construction activities, and the lower picture shows actual execution. So this open top and parallel construction requires the conditions like very detailed pre-planning, so which requires complicated area handover, and we need a close collaboration of civil side and mechanical, electrical, and HVAC side contractors. And also we need on-time delivery of components. So if we miss the delivery of components on time, then we cannot proceed the work as planned. So there are very many requirements and conditions, but if we can meet these conditions, we will have the advantages of parallel construction work, which can be leveling off the site manpower and shorten construction period, and longer pipe spool lengths, less welding and flange joints, so which can reduce installation and fabrication quantity, and also allow to apply modularization, because we can bring the very big module to the room because the roof is open. And this slide shows development phase activities for construction. So project development phase work product will be integrated data management through total plant life. So this is a 3D plant CAE, and integrated plant construction methodologies and management. And also advanced site-specific design engineering before starting construction. So this is crucial to make an on-time and on-budget project by less rework during construction. So during engineering phase, hundreds of engineers will work on the development, the plant design, but once we enter into the construction phase, thousands of people will work on site. So to complete design work before start the construction will be a very important feature for this kind of very big construction project. So construction and component installation are performed as designed and planned during the development phase. So this is our strategy and what we want to achieve. And on this slide, I would like to touch on UK Horizon project. So this is a bitter experience for Hitachi in terms of the financial aspect, because we gave up this project in 2019, so which is just before achieving FID. But this is a good lesson learned as a whole for our company. And the starting point is the 2012. So at that time, after Fukushima accident in 2011, we have had to find a project to keep our resources, knowledges, and capabilities in overseas. And we found this UK Horizon project. So October 2012, Hitachi acquired Horizon Nuclear Power from RWE and E.ON. And next year, April 2013, Hitachi-GE applied for UK BWR GDA. So this time, Hitachi-GE take a lead of this overseas project. So if we agree with GE Hitachi, we can take a lead this kind of overseas project as a main contractor. And in July 2016, Horizon, JAPC, Japan Atomic Power Company, and Hitachi signed a cooperation deal. And next year, Horizon and Exelon, this is now Constellation, partnered to advance Horizon project. So because Horizon was a kind of a special purpose company, so we had to develop the capability of utility from scratch. So we needed the very strong support and help from the very knowledgeable and experienced utilities. So that's why we made a cooperation agreement with these two companies. And then next year, December 2017, HGNE successfully completed the UK ABWR GDA, which was planned. So this is a big achievement of the project. And then June 2018, UK government announced to start the discussions about the status and progress toward FID. But in January 2019, Hitachi suspended Horizon project from the viewpoint of its economic rationality as a private enterprise. And then March 2020, Hitachi ended business operation on Horizon project. So Hitachi withdrew from Horizon project as a financial structure for the project was not agreed among the parties concerned during its project development phase. So the main lessons learned is that this was the first time for Hitachi to take 3 different roles. So one is the EPC contractor, and the second is key component supplier, and the third one is owner and client of project. so which is driven by Horizon. And we found that the Japanese utilities experience and capabilities are very important to make a successful project. So in the Japanese experience, integrated team is very crucial for successful project. But the utilities take a very important role. So now from this project, we learned the very important role of utilities again by taking the role of utilities. And also we found that the finance of nuclear power plant is very challenging, especially for large water reactor type, because it requires more than 10 billion pounds for 2 reactors. And of course, only Hitachi cannot provide such huge investment. So we talked with many potential investors, but we found that investors' risk perception of large reactor construction project was very, very high. And we tried to achieve the competitive levelized cost of electricity, and the main factor of driving up of the cost of electricity was discount rate, so which reflects the risk of the project. So we learned that the successful project, which was demonstrated already somewhere in the world, will be very important for potential investors to see the project viability. And if the risk perception is low, then which drives the discount rate lower, so which makes lower electricity cost. So this is one of the lessons learned I had in this project. And also during Horizon project, Horizon and Hitachi have investigated UK supply chains and scopes. And this slide shows UK ABWR licensing activities. So Hitachi-GE applied to the UK Regulatory Authority, ONR, and the Environmental Agency for the GDA of the ABWR in April 2013. And GDA was completed in December 2017, which was as planned. So this is a key milestone of the Horizon UK project. So we prepared a lot of application forms and safety analysis, regulatory compliance, and support documents. So this is one of the very important assets of the project. Now ABWR is certified in UK, US, Taiwan, and Japan. So now I move on to the overview of BWR X300 and our contribution to the project. This is the overview of BWR X300. So this is a 300 megawatt and jointly developed by GE Hitachi and Hitachi-GE. And this reactor is based on ES BWR, which was licensed by US NRC, and cost reduction by significant simplification to overcome scale demerit. So in general, the smaller reactor is disadvantage in terms of economics, but by simplifying the many systems and features with good safety features, we are trying to overcome this scale demerit. And utilizing proven and reliable components with innovative safety system. So this is also important aspect. So this BWR X300 is based on existing BWR technologies and constructability integrated into design. So we are applying modules into BWR X300 design. And this is key features of BWR X300. Small light water reactor with enhanced safety economy and construction and flexibility. So we have innovative safety system such as the isolation valve integrated directly attached to RPV to reduce rocker, and isolation condenser system, the passive cooling system, to keep 7 days cooling without power actions. And we apply modularizations to achieve shortened construction period. And also by simplifying the systems, we try to make cost reduction, competitive construction cost. And also we have flexibility features in terms of operation and siting. And this is our leading projects. The first project is in Canada. So Ontario Power Generation in Canada, and SNC Lavalin, which is now Atkins Realis, and AECON, this is a construction company, have signed a contract for the deployment of BWR X300 at Darlington site. So this is the first commercial contract for a grid-scale SMR in North America. And this is to be deployed by 2029. And we expect the FID will be achieved early next year. So this year is very crucial moment for this Canadian project. And also we have United States project led by TVA. So this project is already touched in the previous presentation, so I don't get into the detail, but we have a project in United States. And also we made a technical collaboration agreement between TVA, OPG, and Shinsos Green Energy. This is a parent company of OSGE and GE Hitachi. So this agreement is to develop the standard design of BWR X300, which can be licensed and deployed in Canada, United States, and Poland, and beyond, like Estonia. And Hitachi-GE is participating this standard design activities by GE Hitachi. And this slide shows global interest in BWR X300. So of course, the Fermi Energia is part of the potential owner of BWR X300. And in Poland, we have Oren Shinsos Green Energy, and in Canada, Sweden, many companies are now interested in BWR X300. So I think the first project is crucial to realize these future projects. And HGNE, we are dispatching our engineers to this standard design project. And also, I would like to touch on briefly about this European Industrial Alliance on SMRs. So together with Fermi Energia and GE Hitachi, Hitachi Europe is also participating in this alliance activities. So our colleagues in Poland are joining these activities. So I hope there will be good interactions between these companies for the future deployment of BWR 300 in Europe. And also, I would like to briefly touch on the Hitachi Group potential contribution to BWR 300 project. So GH will take lead of overseas projects, including European region, and HGNE will work together with GH as a joint developer of BWR 300. And in addition, Hitachi Europe Poland branch has signed an MOU with OSGE to provide some contribution to BWR 300 project. So as a whole company, we would like to make a good contribution to BWR 300. And this slide shows HGNE's contribution to BWR 300 projects. So by utilizing HGNE's engineering, manufacturing, and construction capability and experience through GH, we support GH as a joint developer of BWR 300 in the engineering support and demonstration test. We have testing facility in Japan, so we contribute to this demonstration test and also provide the following in accordance with the agreement between GH and HGNE, so such as supply of critical reactor components and construction support, including application of modularization. So we need this kind of support project to keep our resources and knowledge, to keep our suppliers. So this is a very good opportunity for us to keep our supply chain in the future. So we can supply these reactor components because the reactor internals and fine FMCRD are almost same in the BWR 300. So we can leverage the ABWR manufacturing experience into this BWR 300. And this is BWR support for construction. So as we have many experiences in Japanese projects, we can contribute in consideration of the modularization lessons learned, so we can maximize specific benefits into the small reactors for factory fabrication, consideration of inland transportation, and small reactor building and or containment by rationalizing system and components. So this is a summary of my presentation. So we, Hitachi-GE, delivered successful projects delivery in Japan. So Hitachi-GE has a track records of on schedule and on budget ABWR projects in Japan by applying improve on-site productivity, reduce on-site work, leveling on-site work, and improve site support work efficiency. So this successful project delivery have been achieved by integrated project delivery team, which consists of utilities, reactor vendors, construction companies, and suppliers. So this is the good track records of Japanese experience, and HGNE would like to bring this experience into the BWR 300 projects. So HGNE support GH as a joint developer of BWR 300 by utilizing HGNE's engineering, manufacturing, and construction capability and experience. Hitachi Group also seek for potential contribution to BWR 300 related to non-nuclear scope, and supply chain development will be very important aspect for deployment of SMRs in Europe, because we have very strong supply chain in Japan. But if we try to bring this plant to other part, we need to develop the good supply chains in such regions. So this is a challenge, but we would like to, HGNE would like to support and contribute for this BWR X300 projects. So this is the end of my presentation. Thank you for your kind attention.
Is there any questions?
How do you see, are you willing to cooperate with local subcontractors as well? Like, can Estonian companies help you build this?
Yes, of course, we would like to cooperate each other. So the first step is go to the country and investigate what kind of supply chain Estonia has. So it will take a long time, but this is a very important process, and we need local supply chains. So I hope so.
Thank you for the presentation. I just have one question about your expectations. We have in slides you showed two initiatives from the operators and vendor side. One was with the Canadian agreement, Canada, then was Poland and so on, and one is the European level industrial alliance. What are your expectations about the outcomes? What should be the outcome of this initiative? And what kind of impact you see it should have when you're talking about regulator side? Yeah. So what you will do to make our life easier? Okay, thanks.
So I understand each regulator should be independent, but so standard design is for the not site or country specific design, but can be applied to many countries as a basis. And United States and Canadian regulators are working together. So I hope this kind of activities will keep going on and involving the vendor side as well to establish smooth and good regulations. But I'm not an expert, but I hope the better environment will be established. Thank you.
You have a good track record in building in Japan those plants, and now Canada is going to build soon. So my question is, how much are you cooperating with Aecon, the constructor in Canada, and helping them to develop their plans and all this modernization, what they are doing? Because actually 60% of the whole budget is actually the construction. Yeah.
So we have very experienced engineers inside Hitachi-GE, and we send those engineers to the Ontario project and working together with Aecon, OPG, GH, and Atkins Realis, and we are formally organizing the PMT. So it's a project management leadership group, and the HGNE engineers are part of that team. So we are actively involving.
Okay. Thank you. Thank you for detailed information.
Thank you.
Yeah.